All right, so right now what we're going to talk about is section 5.6, and this is actually a cute little section. I think you're going to really like it. Okay, what we want to do is talk about the average value of a function. So the first question I wrote on the board is, how do we find the average of n numbers? And I think you all know this. What you do is you add up all of the numbers and then divide by n, the total number of things that you added. So then our next question to ask is, okay, let's change this scenario. How do we find the average value of a function? Well, what we can say is, let's choose some interval in there and look at the function values at regularly spaced x values. The thing is, there's infinitely many function values between those two values. I mean, there's infinitely many numbers between just 0 and 1. So what we can say is, well, let's take regularly spaced intervals. Let's divide our interval from a to b in such a way. And then how would we take the average of them? Well, what we would do is add up all of those function values and divide by the number of values that we added together. Okay? And that can give us an estimate, but clearly it's not a very accurate estimate. Now, over that interval from a to b, I think you would grant me that if we take more function values, our estimate's going to just get more and more accurate. Similar to taking more and more rectangles, our area estimate just gets more and more accurate. What does it mean to take more function values? Well, if n is the number of intervals, we let n go to infinity. Now, some of this is going to start looking very familiar to you. So what are we going to do? We consider a function on the interval from a to b. And our goal is to find the average value of that function on this closed bounded interval. So what we do is we divide it into n different subintervals, and the length of each subinterval is delta x. Okay? So since they're of equal length, what you do is you take b minus a over n. Now, what I wrote down here is going to play some relevance in just a little bit. I think you could grant me that we can rewrite this term in terms of n, right? You multiply both sides by n and then divide both sides by delta x. Okay? So, once we've done that, what does that give us? Well, that tells us then that the average value of our function is going to be equal to the limit as n goes to infinity of our function value at our first point, our second point, all the way across the board, and then divide by n. Okay? Again, we're just taking the average, and then we're letting that number n go to infinity. Well, the first thing that I'm going to do is rewrite this in that sigma notation that I showed you. When you're adding a bunch of things together, we can say it's the limit as n goes to infinity of f of x, I from 1 to n of my function values, and we can put that over n. Now what I'm going to do is rewrite that using this. So we get the limit as n goes to infinity of that sum. And in place of n, that's b minus a over delta x. Okay? We don't like things written like that. When you divide by a fraction, what we do is we multiply by the reciprocal. So now let's just clean this up algebraically. And let's say that this is then going to be equal to the limit as n goes to infinity of that sum from 1 to n of f of x sub I. And again, What I'm going to do is invert and multiply, so that's times delta x all over b minus a. Okay, first off, this b minus a is not relevant for my limit, so I could say that's 1 over b minus a times the limit as n goes to infinity of the sum from 1 to n of my function values times delta x. Now let's stop for a second, okay? I'm hoping that this is going to ring a bell to you and look familiar to you, because I claim that we've played with this before, okay? When you take the limit of this sum, notice it's function values times the length of each subinterval. Start thinking about areas of rectangles. This is our Riemann sum. So, by definition, the average value of a function from a to b is 1 over b minus a, and this, by definition, is my definite integral of that function. Now, I could have just given you that formula and said, okay, here's how you find the average value of a function. But I really enjoy showing you guys where formulas come from. I think it's really important. And this formula came straight from knowing how to take the average of some numbers and then relating this to the fact that that's a Riemann sum, which by definition is our definite integral. All right, how do you know when to use this formula? Well, when they ask you to find the average value, that's a pretty good indicator. So what I'd like to do now is play with a few different examples. And each example is going to look slightly different from another. Okay? So the first example that I would like to do is just say, all right, let's find the average value of, say, f of x is x squared minus 2x plus 5. And let's just make life a little easier for ourselves and say from x equals 0 to x equals 2. Okay, well, this is pretty much just a plug and chug at this point. This is my a value, this is my b value, so it's 1 over 2 minus 0, which is 2. Times the integral from 0 to 2 of my function. And this is certainly something that we can evaluate. Okay, we have 1/2. Now let's take our antiderivative. We have x cubed over 3 minus 2x squared over 2 plus 5x, which we're going to evaluate from 0 to 2. Notice I started making life a little easier for ourselves by having us look from 0 to 2. Again, we have a polynomial, so the 0 is pretty sweet. Okay, again, we have 1/2, and then we're going to take f of 2 minus f of 0. Okay, if I plug 2 in, I have 2 cubed over 3. Again, those cancel, so minus 2 squared plus 5 times 2. And I think you'll grant me, plugging 0 in there, everything just goes away. So what do we have? 1/2, well, we have 8/3 minus 4 plus 10. So we have 1/2 times 8/3 plus 6, which is 18/3. So we have 1/2 times 26/3. So the average value of our function over that interval is 13/3. All right. Now let's take something perhaps a little more applicable. What if I told you that the population of the world T years after 2010, notice T is the number of years after 2010, is predicted to be P equals 6.9 e to the 0.012 t billion people. Okay, well, I'm going to ask two questions. What is the population predicted to be in 2020? Well, notice I'm not asking for any average. I just want to know what the predicted population in the year 2020 is going to be. That's just a matter of plugging that into our function. So we want to know the population, 6.9 e to the 0.012. And what do we plug in for t? Well, notice t is the number of years after 2010. And so t is equal to 10 here. So if we compute that, what we get is about 7.8 billion people. That is a lot of people. Yikes. All right. Well, what if now I asked a somewhat different question? What if now I asked, what is the predicted average population between 2010 and 2020? Now what I'm asking is different here, okay? Notice I want the average population. So this is where we're going to use our average value formula. Well, we've got to translate this. Notice in 2010, t equals 0, and in 2020, t equals 10. So we'll use our formula. It's 1 over 10 minus 0, which is 1 over 10, times the integral from 0 to 10 of 6.9 e to the 0.012 t dt. All right, we can certainly do this. We're going to have 1/10. Take the antiderivative, we get 6.9 e to the 0.012 t divided by 0.012, and we're going to evaluate that then from 0 to 10. Notice we have an exponential function, so we do have to pay attention to our 0 here. All right, now I know we all know how to compute this, but curiosity has gotten the better of me, so let's actually see what we get. 1/10, and again, what do? We plug in 10, subtract off what we get when we plug in 0. So we have 6.9 e to the 0.012 times 10 divided by 0.012 minus, well, notice when we plug 0 in here, e to the 0 is 1, so we're just dividing by 6.9 over 0.012. Alrighty, so let us compute what we get here. We have 6.9 divided by 0.012 times e to the 0.12 power, and then we'll subtract off 6.9 divided by 0.012, and then we'll take that answer and divide everything by 10. So on average, in that 10-year period, there's going to be about 7.3 billion people. All right, let's just do one more example here. And this is a pretty cute little example. Okay? What if now I want you to do this, or us, I should say. Find the value of b, and I'm going to tell you b is greater than 0, so that the average value of f of x equaling x squared plus 1 from 0 to b is 28. All right. So how do we go about this? What I would recommend you do is first notice you're finding the average value of a function, so we already know to use that formula, okay? The thing is, what we're looking for is different because, excuse me, we're actually given the average value. Don't we have 1 over, well, b minus 0 is simply b. 1 over b times the definite integral from 0 to b of x squared plus 1 dx. We know that's 28. Okay? This is what the statement of the problem gave us. Okay? What we need to do is find the value of b. How do we go about doing that? Well, let's follow our noses here. Okay? I see a definite integral. I'm totally all about taking my definite integral. So let's watch this. We have 1 over b. And let's take the antiderivative here. We have x cubed over 3 plus x. And then we evaluate that from 0 to b. And again, we know that that's 28. All right, well, when you evaluate something from 0 to b, what does that mean? It means you take your function value at b minus your function value at 0. Notice we have a polynomial here, so when we plug in 0, we just get 0. So we have 1 over b, and when we plug b in here, we have b cubed over 3 plus b, and we know that that's equal to 28. Well, we can distribute the 1 over b, and I claim what we get is 1/3 b squared plus 1. Okay, that goes in there. We have 2 left, and those just cancel off, and we get the 1 equals 28. Is that something we can solve? Totally. Okay, what do we have? We have 1/3 b squared plus 1 is 28. We can solve this for b for sure. Numbers are even really sweet. Okay, first we'll scoot our 1 over. We have 1/3 b squared is 27. Okay, we want to get b alone. We'll multiply both sides by 3, so we get b squared is 81. And we take the square root of both sides, and we get b is plus or minus 9. Notice we were given the parameter that b is greater than 0. Therefore, we know b is equal to 9. Isn't that fun? All right, thank you.